So if anybody needs help with the prerequisite for the oral exam on projectile motion, just the conceptual part, here's your help file. So definition of projectile motion. It's free fall while moving horizontally with a constant velocity. That's what projectile motion is. We assume no air resistance, therefore there is no acceleration horizontally. So a projectile that is launched, it could be launched horizontally to begin with, it can be launched at an angle, as long as it has initial velocity that is horizontal and starts falling down vertically. Even if it's tossed upward, it will still have acceleration of negative 9.8 meters per second squared downward due to gravity. That would be projectile motion. Acceleration of projectile motion, any part of its trajectory, doesn't matter if it's on at the very beginning, after it's just been launched, if it's at the top of the trajectory, if it's on the way down, it does not matter. The projectile has a downward acceleration, no horizontal acceleration, only the downward acceleration. So it's directed downward and is equal to 9.81 or 9.8 meters per second squared. If you want to call it negative, go for it. The important part that it is downward. A horizontally launched projectile has only horizontal initial velocity. You can say v initial y equals 0 because a horizontally launched projectile starts moving like that, and that just moves down. A horizontally launched projectile has an acceleration of 9.8 meters per second squared, 9.81 if you want, directed downward. Again, it doesn't matter how a projectile was launched, it will always have a negative acceleration directed straight downward. Two projectiles launched from the same height horizontally will spend the same amount of time, or you can say at the same time in the air. Example 1. This is like the marker lab that we had together at one of the first classes on projectile motion. So two markers launched horizontally from the same height. So since they're v initial y purple, v initial y green equal each other and equal 0, then they only have vx. You know the formula for vertical displacement is v initial y change in t plus 1/2 gt squared. If you have initial velocity y to be equal 0, then this just goes away and you have change in y equals 1/2 gt squared, from where change in t is going to be root of 2 change in y over g. Or you can do change in y, you can also do change in y over g halved. Either way, you will have the same amount of time that the two markers spent in the air. The fact that the purple marker and the green marker land at different distances horizontally only means that Vx of the green marker is greater than Vx of the purple marker. How much greater? Well, if the delta x is double of what the purple marker had, that tells you that Vx green was twice the Vx purple. So for example, if one of the markers lands 3 times farther, that means that it's 3 times faster horizontally. Again, that only happens if they both were launched horizontally from the same height. When two projectiles are launched horizontally from the same height, the one with double the launching speed will land double the horizontal distance. If you change this to 5 times, then this would be times 5. So the factor of the speed is the factor of the distance horizontal, delta x, and it works backwards the same way. The purple and green marker are flicked off the same table. If the purple marker is flicked 3 times as fast as the green marker, and it's landed 1.2 meters from the edge. So I can say my Vx of purple compared to Vx of green. That's what I'm after. What is the landing distance of the green marker? Explain your answer. So if I have purple being 3 times the speed of the green, change in t is the same. Therefore, change in x of purple is going to be V purple x times change in t, which is 3 times Vx of green times change in t. So therefore, if my x of purple is 1.2, then the green would be 1/3 of that. This would be 3 times change in x of green. So therefore, x of green is going to be only 0.4 meters. Draw x of t, v of t, and a of t for the horizontal and vertical parts of motion 6 graphs. I'm going to pause and draw. You also pause the video and then draw them yourselves. I hope you have something that looks somewhat what I'm showing you. For horizontal part of the motion, we know that velocity doesn't change. Hence this. This right here is a constant positive velocity. We're not falling down. We're just moving to the right, forward, north, south, doesn't matter. We're moving forward in the positive direction. And since there's no air resistance, velocity doesn't change. Because velocity is constant and positive, that's what we have for x. We have a constant positive slope in x versus t. And then there is no acceleration, so these should be all showing a constant velocity in the positive direction. Now, vertical part of the motion, here we have this half of a parabola pointing down. It's speeding up on the way down. We have 1/2 gt squared. Part of the parabola, because time doesn't go backwards, we don't have the negative part of the parabola, only the positive part of the parabola. And it's pointing downwards because if we have a horizontally launched projectile, it's going to be falling down while moving to the right or forward horizontally with a constant velocity. So that's for horizontal part. This is for vertical part. It's moving with acceleration. Since it's moving with a constant negative acceleration, hence this. Because it's launched at horizontal velocity only, initial velocity vertical is 0. And then it just starts speeding up and up and up and up. And if I had numbers, this slope right here would have been negative 9.8 because that's the acceleration. And then right here, this would have been negative 9.8. Now we're moving on to the projectile launched at an angle. So when we have an angle, we are given initial velocity, then we know we can have something like this. If I have v initial and an angle, theta, for example, then I can say that my vx is going to be v initial times cosine of theta. V initial y is going to be the v initial times sine of theta. Notice that Vx doesn't have the initial, and that's again because it doesn't change. Remember, it's just constant V in the horizontal direction. But Vy is going to be changing, and we have initially, because we launched it at an angle, no longer horizontally, we will have initial velocity, which is pointing upwards, which is here. Vy initial. And this will just be Vx. Which velocity will remain the same throughout the trajectory of motion? Horizontal. So that's your answer to this, horizontal. And then vertical velocity will become 0 at the top and negative when projectile falls back down. And that negative will be equal to negative v initial y. Now, if two projectiles have different launching velocities, how will you determine which projectile will spend more time in the air? So if you look at my triangle here, I have the Vy and Vx. That is responsible for the time in the air is the Vy initial. If you have V initial 1 times sine of theta 1 versus V initial 2 times sine of theta 2, that's what you're going to compare. So, for example, if you have V initial equals 45 meters per second at 15 degrees versus V initial, that's 1 and that's 2, 40 meters per second at 20 degrees, you cannot just look at them and say, oh, this one will be. Not really, because this is greater velocity but at a smaller angle. This is smaller velocity but at a greater angle. So before you can make a verdict about which one stays in the air longer, take the 45 and multiply by sine of 15 and then compare it to 40 sine of 20. And then see which one is greater. And the one that is greater will stay in the air longest. Now rank the following projectiles from shortest to longest so that, again, you will be multiplying 50 times sine of 12. Then you're going to do 23 sine of 60. You're going to do 35 sine of 28 and 42 sine of 30. And then you're just going to rank them from the greatest to the lowest. Now rank the speed at the top. Speed at the top, if you remember what happens at the top, so right here, if you had V initial Y at the top, you don't have it anymore, but you still have Vx. So at the top, Velocity is just the horizontal component. What you're going to do, you're going to take 50 cosine of 12. Then you're going to take 23 cosine of 60, 35 cosine of 28, and then 42 cosine of 30. What you're going to be looking at is the horizontal component of your velocity, and then you're just going to rank them from the smallest to the greatest. And we need to draw six graphs, 3 for horizontal and 3 for vertical, for a projectile that is launched at initial angle. So it's no longer horizontal, it actually has an angle. So I'm going to stop, let you finish that, and then we will compare. So you pause this video, draw those graphs, and compare. All right, here are the graphs. The first part, the horizontal part, did not change at all. We still have positive velocity, constant rate. So this represents constant rate. This is constant positive velocity in the horizontal direction, still no acceleration. What changed, instead of a half of a parabola, you now have a full parabola, because your object is going to go slow down on the way up, stop, and speed back up on the way down. Velocity is now, we have initial velocity, then it will stop, and then it will speed back down. So this would be v initial, v final, opposite each other. And then acceleration is still negative 9.8, the way it was before. And then I will just complete example 5. Be prepared. If I see them exactly in your submitted form, I will not take it. I do not need you to copy me. I need you to follow this through and then make up your own examples. Okay, this is only fair. 23.7 meters per second at 41 degrees to the horizontal. Acceleration right after the launch, negative 9.81 meters per second. I technically don't have to say that it is negative. I'm just going to say 9.81 directed down. Acceleration at the top, 9.81 meters per second squared directed down. Acceleration right before it hits the ground, 9.81 meters per second squared directed down. Speed at the top is going to be 23.7 cosine of 41, whatever that number is, meters per second. Time to the top. So you remember the acceleration formula is v final y minus v initial y over change in t. And if I say that change in t is half time, then I can say negative 9.81 equals 0 minus 23.7 sine of 41 divided by change in t. That's how I can find my half time. So then I will replace them. 23.7 sine of 41 divided by 9.81. Or you can do just 9.8. That's fine as well. Final speed when it hits the ground. The speed will be the same. It is going to be 23.7 meters per second, because we assume there's no air resistance, there's no loss of energy. Velocity is not going to be the same. Velocity, if I asked you for velocity, you would say that it is 23.7 at 41 degrees below, not above to the horizontal, but below the horizontal, or like some of our students like to say, into the ground.